Good day, students. Welcome to a real quick review to the Limits Chapter 2 test. We're going to be going over the solutions real quick. If you like much more detailed and slow explanations to the problems we're doing, feel free to visit our website at math.serp.com and look under limits. All right, let's take a look at question number 1. We're to find the limit as x approaches -3 of x squared plus 9 divided by x minus 3. Okay, some students might get tempted to factor the numerator. This is not a difference of squares, so you cannot factor it. We can just substitute directly here, and we'll have -3 squared plus 9 divided by -3 minus 3. 3 squared, -3 squared is 9 plus 9. We have 18. And then -3 minus 3 is -6. 18 divided by -6 is -3. All right, let's take a look at question number 2. We're to find the limit as x approaches -3 of 3 over x plus 1 divided by 3x plus x squared. Now we can see that if we plug in -3 into the denominator, we'll have -9 plus 9, which results in a 0 in the denominator. Hence, we can't solve it that way. Okay, so what we just have to do is try and combine the fraction in the numerator, put it 1 over 1, and then we can times this by x, top and bottom. And then we have, in the numerator, we have 3 plus x can be written as x plus 3 over x. And then that divided by, you can factor out x from the bottom, x times x plus 3. All right, if you write the denominator over 1, we can multiply the numerator, x plus 3 over x, by the reciprocal of the denominator, 1 over x times x plus 3. The x plus 3's cancel out. You end up with 1 over x squared. So we can just take the limit of that. So we take the limit as x approaches -3 of 1 over x squared, and then you have 1 over -3 squared, and that's simply 1 over 9. All right, so there goes the answer. Let's take a look at question number 3. For question 3, we have to find the limit as x approaches 0 of -2 sine to the third x over x to the third. Okay, so this one involves using the sandwich or squeeze theorem 3 times. We can factor out the negative and then write this as the limit as x approaches 0 of, or also we can factor out the 2. Okay, so we have sine x over x times sine x over x times sine x over x. If you take the limit as x approaches 0 of all these 3, they're all going to be 1. So you have -2 times 1 times 1 times 1, and the answer is -2. All right, let's take a look at question number 4. We're to find the limit as x approaches infinity of the square root of 49 x squared minus 2x. 2x minus 7x. All right, we can simply plug in infinity here to see what happens. So if we plug in infinity here, we're going to have the square root of infinity minus infinity minus infinity, and this is an indeterminate form. We don't really know how fast the different infinities are growing, so we can't really figure out what this limit is by direct substitution. So what we're just going to do is we're going to rationalize the numerator. So let's go ahead and rationalize the numerator. We have the square root of 49 x squared minus 2x minus 7x. So multiply the top and bottom by the square root of 49 x squared minus 2x plus 7x. On the top and on the bottom, the same story. Let's write this over 1. And then this over square root of 49 x squared minus 2x plus 7x. All right, when you're done working it out, in the numerator, you're going to have 49 x squared minus 2x minus 49x squared, and then that entire thing divided by, in the denominator we'll simply have the square root of 49x squared minus 2x plus 7x. Okay, in the numerator these two cancel out, and then what we'll be left with, we want to find a limit as x approaches infinity of negative 2x over the square root of 49x squared minus 2x plus 7x. Okay, so we're going to look at the fastest growing on the top and on the bottom. In the denominator, the fastest growing will be 7x and the square root of 49x squared. And the numerator is just simply negative 2x. So we have the limit as x approaches infinity of negative 2x over the square root of 49x squared is 7x plus 7x. That equals, it's going to be the limit as x approaches infinity of negative 2x over 14x, and then divide the top and bottom by 2x. We have the limit as x approaches infinity of negative 1 over 7, and your final answer is negative 1 over 7. Alright, so for number 5, we have a piecewise defined function, and we are asked to find if the limit as x approaches negative 2 exists. So let's go ahead and write down the piecewise defined function. We have f of x equals 3x squared plus 5, and then 17, and then 2x to the third plus 1. And then this is for x less than negative 2. This is when x is equal to negative 2, and then this is when x is greater than negative 2. So the limit as x approaches negative 2 involves just finding the left and the right hand limit, okay? So the limit as x approaches negative 2 from the right of the function is going to be what? So let's go ahead and sketch a number line to help us visualize the situation. You have a number line. The breaking point is negative 2. So we have negative 2. To the left is 3x squared plus 5. And then to the right is 2x to the third plus 1. So approaching from the right, we're going to take this function. We're going to be looking at the limit as x approaches negative 2 from the right of 2x to the third plus 1. So we'll simply plug in 2 into this expression. And we plug in 2, we have negative 2 to the third. Negative 2 to the third is negative 8 times 2 is going to be negative 16 plus 1, which is negative 15. That's the right-hand limit. And then for the left-hand limit, limit as x approaches 2 from the left of the function, we're going to be looking at the limit as x approaches 2 from the left of the quadratic function expression, 3x squared plus 5. I will plug in 2 from the negative 2 from the right. From the left, we'll have 3 times negative 2 squared plus 5. And then if we work that out, this is 4 times 3, 12 plus 5 is 17. So since the left and the right-hand limits are different, the limit does not exist. Okay, so since the limit as x approaches 2 from the left of the function is not equal to the limit as x approaches 2 from the right of the function, that implies that the double-sided limit, the limit as x approaches 2 of the function, does not exist. All right? All right, let's take a look at question number 6. So for question 6, we're to find the limit as x approaches negative infinity of the cube root of 8x to the second power minus 3x to the third minus x to the sixth divided by x times x plus 5 times x minus 2. Okay? All right, so what we're going to do is take a look at the leading coefficient in the numerator and that in the denominator. That will tell us the growth rate upstairs and downstairs. In the numerator, we are looking at the sixth root of the third root of negative x to the sixth, and in the denominator, we just multiply x, and x. Okay, so we're going to be looking at the third root of negative x to the sixth divided by, in the denominator, x to the third. All right, if you simplify that, you're going to have limit as x approaches. Actually, this is a plus, so that makes us a plus. So limit as x approaches negative infinity, the third root of x to the sixth, you just divide the power by 3, which is 2x squared over x to the third. And then this simplifies into limit as x approaches negative infinity of 1 over x. When you plug in infinity, you have 1 over negative infinity, which is equal to 0. So there goes your answer. All right, let's take a look at question number 7. So question 7, we are to find the limit as x approaches pi of 3 int x over 2. So we can find this by direct substitution. We're going to have 3 int of pi over 2. We know what pi is. Pi can be considered 3.14. So 3 int of 3.14 over 2. Okay, we know what the int function does. It rounds down. So int of 3.14 rounded down is going to be 3. So we have 3 times 3 over 2. 3 times 3 is 9. 9 over 2 is our final answer. All right, let's take a look at question number 8. So question 8, we to find the limit as x approaches 4 from the right of the absolute value of x minus 4 over x to the third minus 64. Okay, since we're coming from the right, then we have the limit as x approaches 4 from the right. This absolute value becomes positive, x minus 4. And then if we use the difference of cubes formula to factor the denominator, we have x minus the third root of 64 is 4, since 4 to the third is 64. X minus 4x plus 4x plus 16. Okay, these two cancel out. And then we're just simply looking for the limit as x approaches 4 from the right of 1 divided by x. This is supposed to be x squared plus 4x plus 16. And then we just simply plug in 4 into the x's. So we are going to have 1 over 4 squared plus 4 times 4 plus 16. That's 16 times 3, 1 over 48. That's your final answer. All right, let's take a look at question number 9. We're to find the value of a. Find the value of a so that the function f of x equals ax minus 3. Ax minus 3 when x is less than or equal to negative 2, or 3x minus 3 if x is greater than negative 2. Find the value of a so that this function is continuous. Okay? All right, so in order for the function to be continuous, the left and the right hand limit has to be equal to the value of the function at that value, at negative 2 namely. So in this case, the limit as x approaches 2, negative 2 from the left of the function has to be equal to the limit as x approaches negative 2 from the right of the function. The value of the function is equal to the left-hand limit since this line is included there. Okay, so this is sufficient. So what we're going to do here is simply, let's draw a number line so we can get our orientation together. Draw a number line. We have two functions, one to the left and one to the right. So this is negative 2 to the right. We have 3x minus 3. And then to the left, including the point, which is the value of the function, we have ax minus 3. Okay, so the left-hand limit is basically the limit as x approaches -2 from the left of ax minus 3, and then that has to equal to the limit as x approaches -2 from the right of the right-hand function, which is 3x minus 3. Okay, so we'll plug it in, plug x in -2 into the x's. We'll have a times -2 minus 3 equals 3 times -2 minus 3. I'm going to simplify that. We have -2a minus 3 equals -6 minus 6. That's -9. If you add 6 to both sides, add 3 to both sides, you have -6. Divide both sides by -2. A equals 3. All right, so there goes your final answer. Now let's take a look at question number 10. Question number 10, we were asked to find and classify all discontinuities. Find and classify all discontinuities for the rational function f of x equals 3x squared minus 7x minus 6 divided by 2x to the third minus 18x. Okay, let's go ahead and factor both of them. Start with the numerator. The numerator is a quadratic trinomial, so we can factor it by grouping using the x gain. So make our x. AC in this case is -18, and then b is -7. The two numbers that work are -9 and 2. These two multiply to give you the top and add to give you the bottom. All right, so we have 3x squared minus 9x plus 2x minus 6. We divvy it up the center and factor by grouping. Okay, so from the first two, we can factor out 3x. Take out 3x. We have x minus 3. And then from here, we can take out 2. And we have x minus 3. So the factored form is x minus 3 times 3x plus 2. All right, and then for the denominator, let's go ahead and factor that also. We have 2x to the third minus 18x. We can factor out 2x, so we have 2x times x squared minus 9. This is the difference of squares, factors into x plus 3 times x minus 3. All right, so the original function in its factored form is x minus 3 times 3x plus 2 divided by the factored form of the denominator, which is 2x times x plus 3 times x minus 3. Okay? Now, any factor that factors out, that we can cancel out, those are the removable discontinuities. Okay? So notice we can cancel out x minus 3. So our removable discontinuities, removable discontinuities are what you get when you solve this. And then x equals 3 is our only removable discontinuity. Okay? And then our infinite discontinuity are the ones that cannot cancel out in the denominator. Okay? Those are the ones that make our expression undefined. All right? So in the denominator, we can see that we have two infinite discontinuities. We have to solve 2x equals 0 and x plus 3 equals 0. All right? If you solve this, you have x equals 0. If you solve this one, you have x equals -3. So these two are your infinite discontinuities. Okay? Infinite discontinuities here, removable discontinuity right there. All right, let's take a look at question number 11. So question 11, we're to find the limit as x approaches 3 from the left of x plus 3 over x squared minus 9. So if you plug in, well, we can factor this, right? So let's go ahead and factor that. X plus 3 over x plus 3 times x minus 3. Limit. X approaches -3 from the left. These two cancel out. So we're going to have limit as x approaches 3 from the left of 1 over x minus 3. And and then plug in 3 from the left, minus 3. That gives us 1 over 0 from the left. So let's go ahead and simplify this. This becomes 1 over negative 1 over infinity, and your final answer is negative infinity. Okay? All right, so for number 12, we are supposed to show, let's go ahead and write that down. So number 12, show that this function, f of x equals the absolute value of x minus 2 is continuous at x equals 2. So all we just have to do is show that the left and the right hand limit is equal to the value of the function. So we have to show that the limit as x approaches 2 from the left of the function is equal to the value of the function at 2, and that is equal to the limit as x approaches 2 of the function from the right. The limit as x approaches 2 from the right of the function. Okay? So these are the 3 conditions that must be met in order to show that the function is continuous. Okay, so let's go ahead and find the first one. Limit as x approaches 2 from the left of the function is going to be the limit as x approaches 2 from the left of the absolute value of x minus 2. Since we're coming from the left, you're going to have limit as x approaches 2 from the left of negative x minus 2. And then we plug in 2 into this function. We have negative 2 from the left minus 2. Okay, so it's negative 2 from the left minus 2, 0 from the left. Opposite of that is simply 0. Okay? All right. And then let's go ahead and evaluate the function at 2. That's the absolute value of 2 minus 2. Let's write that again. Absolute value of 2 minus 2, which is the absolute value of 0, which is equal to 0. And then lastly, limit as x approaches 2 from the right of the function, which is equal to limit as x approaches 2 from the right of the absolute value of x minus 2. Since we are approaching 2 from the right, we're going to have the limit as x approaches 2 from the right of positive x minus 2. And then we plug in 2 from the right. We have 2 from the right minus 2 is equal to 0 from the right. And then that's simply 0. Okay? All right, so the 3 values are equal. So since the limit as x approaches 2 from the left of the function is equal to the value of the function at x equals 2 is equal to the limit as x approaches 2 from the right of the function. That implies that the function is continuous at x equals 2. Okay? All right, so for question 13, we are to find the left and right in behavior models of the function f of x equals the square root of the absolute value of x minus 2 plus log base 3 of the absolute value of 5 minus x plus 2x to the third over 3x minus 5 plus 1 over 3 to the x. All right, let's go ahead and find the right in behavior first. So we're going to take the limit as x approaches infinity of all these 3 functions. So let's go ahead and do that. So for the first one, let's label the functions 1, 2, 3, 4. So for function 1, I want to take the limit as x approaches infinity of the square root of the absolute value of x minus 2. That's going to be the square root of infinity minus 2, absolute value of that. We can clearly see that our answer is going to be infinity. And then for the second function, limit as x approaches infinity of the absolute value of log base 3 times the absolute value of the absolute value of 5 minus x. We have log base 3 of the absolute value of 5 minus infinity. That's simply going to infinity. And then for the third one, the limit as x approaches infinity of 2x to the third over 3x minus 5. we take the fastest on the top and the fastest on the bottom. Limit as x approaches infinity of 2x to the third over 3x. All right, that simplifies. Limit as x approaches infinity into 2x squared over 3. Then when we plug in infinity, we can clearly see that we go to infinity here also. All right, the last one is 1 over 3 to the x. So 4, the limit as x approaches infinity of 1 over 3 to the x. We have 1 over 3 to the infinity, 1 over infinity, which is equal to 0. Okay? All right, so we have 3 functions going to infinity. Question is, which is the fastest growing function? In order, remember our hierarchy for ranking growth rates, we have the logarithmic function, and then we have the power function, and the exponential function, and then we have x to the x. Okay, so this one is the slowest out of all of them. If you compare your radical function and this power function, this function right here is x squared, and this one right here is x to the 1/2 power. At infinity, which one do you think grows quicker? Since this power is bigger, then clearly this function grows faster. Okay, so the right end behavior is basically 2x squared over 3. Okay, so the meaning, what does this mean? The meaning is that the limit as x approaches infinity of the function divided by 2x squared over 3 is going to be equal to 1 because they're the same growth rate. Okay, now let's go ahead and look at the left end behavior. All right, so for the left end behavior, we're going to take the limit of all 3 functions as x approaches negative infinity. Okay, so for the first one, we're going to do the limit as x approaches negative infinity of the square root of x minus 2, absolute value of that. So we're going to have the square root of the absolute value of negative infinity minus 2, which is the square root of infinity, and that's equal to infinity. Second function, limit as x approaches negative infinity of log base 3 of the absolute value of 5 minus x. Let's see what that is. Log base 3 of the absolute value of 5 minus infinity, which is 5 plus infinity. And then that's simply going to be infinity. We're going to find the limit as x approaches negative infinity of the third function is 2x to the third over 3x minus 5. All right, and then we're going to look at the leading coefficient on the top and on the bottom. So we have the limit as x approaches negative infinity of 2x to the third. In the bottom, the leading coefficient is 3x. The leading term on the top and bottom, if you reduce that, you have the limit as x approaches negative infinity of 2x squared over 3. And then if you plug in infinity, you have 2 times negative infinity squared over 3. And then your final answer is 2/3 times infinity, which is infinity. Okay? All right. For the fourth one, I'm going to find the limit as x approaches negative infinity of 1 over 3 to the x. We just substitute. We're going to have 1 over 3 to the negative infinity, which is 3 to the infinity, which is infinity. All right, so if we compare the 3 functions, the fastest growing is the exponential function, of course. So since this is the fastest growing function, the exponential function in your hierarchy, then the left end behavior is 1 over 3 to the x. Okay? All right, let's take a look at question number 14. For question 14, we're to find the limit as x approaches 0 of 4 plus 2x e to the cosine 1 over x using the squeeze theorem, okay? Using the squeeze theorem. Okay, so first of all, we're going to start by looking at what cosine is. Cosine 1 over x, that cosine 1 over x is between two numbers. What value is cosine 1 over x between? We know what the range of the cosine function is, right? Cosine function oscillates between -1 and 1. So the goal is to create this expression right here by using this as the foundation. All right, so let's go ahead and create it. First thing we're going to do is we're going to exponentiate both sides using e as the basis. So we're going to have, on the left side, we have e to the -1 is less than or equal to e to the cosine 1 over x. It's less than or equal to e to the first power. And then I'll multiply both sides by 2, multiply the entire equation by 2x. And then we'll have 2x e to the -1 is less than or equal to 2x e to the cosine 1 over x is less than or equal to 2x e to the 1. And then lastly, we're just going to add 4 to all three sides of our equation. Okay, so add 4 here, add 4 here, and add 4 there. And then you're going to have 4 plus 2x e to the -1 less than or equal to 4 plus 2x e to the cosine 1 over x as less than or equal to 2x e. Let's just write it as 4 plus 2x e so it's consistent across the board. 4 plus 2x e. All right, now we're going to take the limit of all three sides as x approaches infinity. So of the entire expression, we're going to take the limit as x approaches what? 0. Okay? If we do that here, we're going to have 4 plus 0. And then leave the center alone, do not evaluate it. Limit as x approaches 0 for 4 plus 2x e to the cosine 1 over x. And then if you take this limit, you just plug in 0 here. That's 0 is 4 plus 0 also. So what you find out is that 4 bounds this limit. The limit as x approaches 0 of 4 plus 2x e to the cosine 1 over x less than or equal to 4. So by the squeeze theorem, the limit as x approaches 0 of 4 plus 2x e to the cosine 1 over x is equal to 4. Okay? So that's... All right, let's take a look at question 15. For question 15, we are to sketch the graph of the function that meets the given conditions. Limit as x approaches infinity of the function is -2. Limit as x approaches -2 from the left of the function is -3. Limit as x approaches 1 of the function is -infinity. Limit as x approaches -2 from the right of the function is 3. And limit as x approaches -infinity of the function is 0. All right, so to get started, we'll just go ahead and set up our coordinate system and then label it afterwards. So let's draw our y coordinate and our x coordinate. Now we have as horizontal asymptotes because as x approaches -infinity, the function tends towards 0. So we're going to have a horizontal asymptote at the left end because that's where -infinity is located. And then at the right end, we have another horizontal asymptote at -2. So down here, -2, we have a horizontal asymptote. And then at 1, we have limit of x approaching 1. So let's draw a horizontal line right there. That's the value that x is approaching. And then also at -2. Okay, we have another line right here. Okay, so let's go ahead and label what we have. From this direction is -2 from the left. From this direction is -2 from the right. From this direction is 1 from the left, and then on this side is 1 from the right. All right, when we're going to infinity, the function tends towards -2. So it's either on the top or on the bottom. What I'm going to do is I'm going to use the right side limit at x equals 1 to figure out what is going to happen. As x approaches 1, there's no direction here, so this is a double-sided limit. As x approaches 1 from both sides, the function tends towards -infinity. For the x's, this is infinity, and this is -infinity. For the y's, or for the function, upstairs here is infinity, downstairs here is -infinity. So since the function tends towards -infinity as x approaches 1 from both sides, so I'm going to put a portion of the graph here heading downwards towards -infinity, and then another portion here heading towards -infinity. We have a vertical asymptote somewhere here. Okay, so we have a vertical asymptote here and also there. Okay, now let's see. Now we can see that in this piece right here, as x tends towards infinity, we can put a portion of the graph here because we have a horizontal asymptote, and then we can somewhat connect these two. All right. Now we're done with x approaching infinity. That's good. X approaching 1 from both sides. This graph right here and this graph. That's good. Now, as x approaches -2 from the left, you're approaching -3. So 1, 2, 3. So it's kind of like this from the left. Let's make it something like this, approaching -3 from the left. And then as you're approaching -2 from the right, the function approaches 3. 1, 2, 3. So we're getting arbitrarily close. That's why I have an open circle, okay? So I'm going to do it downwards. You know why? Because we have something here. And then as x approaches -infinity, the function approaches 0. So I can put something underneath the horizontal asymptote since I already have a function here, okay? So what we're just going to simply do is connect the dots in whichever way we want. But we want to ensure that the graph is still a function that passes the vertical line test, okay? So I'll just draw it this way, like that. It goes on forever. That's one portion. And then this one, let's see how we can connect it. Just connect it like that. Okay, have a horizontal asymptote there. And then this one, just connect it. Uh-oh, do that again. So we have a horizontal asymptote, and then just try and connect these two lines. It's kind of hard using this device, so we'll just go straight and then just connect it like that. All right, so there goes a possible solution to your graph. Let me make it more asymptotic here. Let's try this again. So goes out and then tends towards your horizontal asymptote, and then starts to just flatten out, okay, like this. Bam. So there goes a possible graph for this situation. So we have -2 from the left, check. -2 from the right, check. X approaching -infinity, check. All the components have been accounted for, and then we're good. So thanks so much for taking the time to watch this presentation. This was a really fast review for those of you who have already mastered limits. If you want a much slower step-by-step explanation, you can go to madcoserve.com under AP Calculus, and you can look at our mixed review videos. They will be much more thorough in explaining the processes for generating the results. Feel free to subscribe to our channel for updates to other great tutorials such as this. And please post a comment to let us know what you think about this tutorial and ways that we can create more great tutorials for you to master mathematics. Thanks again for watching, and have a wonderful day.